So far in Haskell, we've been looking at simple types and writing function types for the types that we're particularly interested in on an ad hoc basis. We've not been worrying about generalizing or abstraction or anything like that. Today though, we're going to look at something called polymorphism. Now, what is polymorphism? A polymorphic function is one which can take many types. You've seen this sort of thing in, for example, things like Java interfaces, when you see the interfaces of type E, and then you instantiate that at runtime with the actual type you're interested in. Now, Haskell is a very neat and compact syntax for doing such things, and we're going to see that today. As a motivating example though, here I have three length functions. One works on strings and tells us the list of strings, or length of a string. One does the same for ints, and one does the same for a list of floats. Now, as you'll notice, the code is exactly the same for each one, which tells us something. It tells us that we're not actually interested in the specific type because the code works the same way for each of them. So there's nothing special about strings that makes the first one the best way to define it for strings, the same for the second one with ints, and the same for the final one with floats. So what do? Well, we can make the type generic so that it will work for any particular list that we are given. How do we do that? Let's define a length function which takes a list, but we need to figure out what this is going to look like. Now, we're still going to be returning an integer because that's the way to represent a length of a list. It's not going to be a float or anything like that, so it should just be an int. But what do we do in here? We have to supply a type for Haskell, but we don't know what the type is. If we want to make this a generic list function or length function that will work for any type of list, how do we do that? Well, what we do is we insert A or B or whatever you want. We just insert a character which represents a random type. So this can be of any type, but we can still instantiate the function in the same way. So we can say that this is going to be equal to 0 when we reach the empty list. And we're going to say that x colon x's is going to be equal to 1 plus length of x's. And you can see that this function is defined in exactly the same way. So actually, yeah, it wants me to use fold_r. I'm going to wrap some brackets around that. But I don't want to use fold_r. So you can see that I can now write the same length function for exactly the same way for any particular type. Now, this is the power of polymorphism. It allows us to define a function once and it can work on any arbitrary type. Now, the reason we can use this is because none of the aspects of the function rely on any particular character or any characteristic of a particular type. The only thing that we're using is the cons function, and if I could stop using caps, if we go into here and we call the type of the cons function, we can say that it is using a generic type as well. So it's saying for any type A, if you give me an element of that type and a list of that type, I will stitch them together to give you a list of that type. So it's not interested in the particular type that it's working with, it will work for any particular type, in the same way that our length function will here. So we can use this function, and we can save this down, and we can load it in. Actually, why am I getting an error? It says error. Because I've got a length defined in the preload, so let's call this length 1. So length 1 is going to be our function, and I'm going to say colon L, this is in week 3 I think, slash polymorphism. So I can load this in, and I can use length 1. I can use it on a string, if I'm interested in strings. I can use it on a list of integers, if I'm so inclined. Actually, let's make this something like that. And it will work for any particular type. So this is the advantage of polymorphism. Now the good thing, the advantage that we have here over say Java, is we can write this once. It's very compact code. It will work for any type that we are interested in giving it. So let's go back to some previous examples and see if we can make their types more generic. So over here, I defined a lot of functions that work on lists. Now in fact, all of these functions can be made more polymorphic. All we have to do is look for the things that restrict the types, and then we can specify where they should be more generic. So here, count character says take a character and a string. But actually, it's only interested in the element being equal to another element. So we can make this more generic. So we can change this to an A, and we can change this to a list of A's. And as long as that type can be compared to itself, then we're happy. So you'll see here it's saying no instance for EQA. This is something we're going to be going on to later in the week, but essentially this means that this type A has to be able to instantiate the equals operator. So what I'm going to say is EQA, and this is saying, okay, give me a type A as long as A instantiates the equality class, and that's where this little operator comes from. In fact, if we go down here and use :I, which I generally tell you not to do, and I use it on equals, you can see that it's part of the class equality A where it does this. So that's why we need this constraint here. Otherwise, we can make this function much more generic. So we take an A that's equatable to itself, and another one, a list of those, and then we return an int. So the only thing that restricts this function is the fact that C can be compared to other elements of itself. So as long as A can be compared to other elements of itself, then we're fine. Some types don't do that, some types do, but as long as it's part of that type class EQA, we're fine. And again, here, all we do is we return the last element, or the second last element of a list. So again, we're not really interested in what the type of that particular list is, because we're just returning a value. So what we can do in here is we can say this is an A, and so is this. Because we're not interested in any properties of the type A, we just take it out and return it. We don't need to care if it's a float, boolean, whatever it is. We can do this for any type. Now down here, we have something else. So we've got reverse a string. So a string takes a string and reverses it, returning the reverse string. Now we're using the cons operator in there, but we know that's pretty generic, so we're not too worried about that. One thing we should be worried about is this. We're using this concatenation operator, so as long as that is a generic, has a generic type, we can also have a generic type in our function, because that's the only possible thing that could restrict us. So let's have a look in GHC and type, and we see that that's also a generic function. That's a polymorphic function that will take any particular input. So again, we don't need to restrict this function for to strings. We can restrict to just type A. So anything that can be put in a list, we are happy with. So we can reverse any list now. We don't have to reverse just strings, we can reverse anything. Similarly, is palindrome. What is this using? Well, it's using the equality type, so as long as the type can be compared to other elements of itself, we're happy. So we can use this trick again, make it part of the equatable type class. That means that it has an instantiation for this type equals, and we can add it. So let's say EQ of A, and then we have the double equals. We take a list of type A, and we return a boolean. We still return a boolean because the output is determined by this double equals here. We're still wanting to return a true or false value if the thing is a palindrome, so we still want to return a boolean, and we can't really make that more generic. We're using the double equals, it returns a boolean, so we are constrained there. And similarly down here, the only restrictions are ones that we've already seen. So we have the plus plus and the cons. So again, this can be turned into a generic type of any arbitrary type A. Now all of these will work. So if I do colon L, and I do week 2, I think it was we saw this, and I do manipulating lists, I can load this in, and we can see that it type checks. And again, I can do is palindrome on any particular string, so I can just type in a random string, but I can also give this a list. So let's give it a list that's clearly not a palindrome. So this is just the list of elements of step size 1 up to 50, clearly not a palindrome, so that's clearly false. However, if we give it the list 1, 2, 2, 1, that is true, because if we reverse it, it is equal to itself. So you can see this polymorphism, by making these types abstract, we allow ourselves much more flexibility and make our code much more powerful. Now we'll be looking at type classes this week. The equatable type class is quite a simple one, so don't worry if you don't understand that though. We'll be going over that in more detail later on in the week. What I really want you to get your head around today is how making these types generic gives our code a lot more power. And really, it's a shortcut for making your life easier, because really you want to be able to say, I don't actually want to care about specifying the particular type here until I have to. I want to write this function once, and then I want to use it on as many types as is humanly possible. But again, that's everything for today. I hope you found this useful. Of course, if you have any questions, you're more than welcome to get in touch. Thanks.